Now let's talk about how to get the calibration file. So to get the calibration file, we have to use a cover slip. So during the data acquisition, what we need to do is we have to put the cover slip here in the source sum. If we pass the if we put the cover slip at the source sum, then what will happen is that, say we are sending light this direction, right? So some of the light will directly pass, but other portion of the light will hit here and it will reflect back here and then again pass. So these two light will make the interference pattern, and this interference pattern will be perfectly sinusoidal. Say for example, the refractive index of this cover slip is n and thickness is d. If we ignore that, there will be no change of refractive index due to different wavelength. Usually if we send the different wavelength through any medium, then the refractive index will be different for different wavelength. But for our calculation, let's assume that the refractive index will not change over our whole bandwidth. Then we will see the cosine form of interference. So the modulation will be perfectly cosine form. And if we look at the spectrum will be look like that. So now one thing that's we need to consider is that although this is for the perfect modulation, but one problem is that in general pixels do not correspond to evenly distributed K, and therefore detected intensity modulation is not perfectly sinusoidal. Although we are supposed to get the perfectly sinusoidal spectrum, but we will not be able to get the perfectly sinusoidal modulation. So we need to somehow correct the wavelength assignment. Now say if we get whatever wavelength we gave, if we do the FFT, then we are supposed to get a peak in G direction for all the A lines. For the sinusoidal wave, we are supposed to get a peak. So one thing we need to do is we have to separate that peak using the band pass filter in Fourier domain. So we will get the peak and we have to separate the peak. And during the peak removal, we have to also remove the DC component. So there will be no DC component, and we'll only only collect the data of the peak of the sinusoidal signal. So ideally, if it is ideal condition, this peak should be purely sinusoidal. So this is our peak. Ideally should be purely sinusoidal, but this is not the case. In real case, this is not the case. So say for example, from the physics we know that if you have a pure sinusoidal wave, then if you plot over time versus phase change, you will find a smooth line. Say for example, we have a sinusoidal signal. Over time it's changing. If we plot the time versus phase change here, and we'll see that it will change purely like straight line. That means phase will change linearly. So we will use this information to correct the wavelength assignment. Say here In this figure, we can see that there is two lines. One is the red line and another is the blue line. Here, red line is our pure sinusoidal line, and we will compare with the actual phase change, actual phase that we will find from our data with this one, and we will see that where we find the non-linearity. If we look at that, the maximum gap between these two lines is at these two ends, and the middle is matching. So there is a mismatch of wavelength assignment in these two ends, this end and that end. So we have to correct. And how we will know that our phase, our assignment is correct? If we see that both of this line, that means our reference line, that is the pure sinusoidal line, sinusoidal phase change line, and the data that will occur, if both of this phase is similar, if they match, then we can say that we have perfectly aligned the wavelength. Otherwise, it's not true that we have aligned the wavelength. So to do that, say we define a wavelength W, and we will use this to interpolate the fringe that we will collect from our setup, so that our K value is evenly spaced. But even though after doing that, what we will do is from our phase data, from the phase data, under phase data, we will fit with the third order polynomial, and we will check the difference between the fitted data and our normal under phase data, and we will see the mismatch all over the place. Especially we see the huge amount of mismatch at the here and here, bottom to corner. So we can assume that this mismatch is coming for the non-linearity. That means this mismatch is coming because wavelength is not assigned properly. This is due to the wrong wavelength assignment. So we have to correct for that. And also we can calculate the error, like how much error in this mismatch. You can see here the error. So one way to do that is, say for example, we'll define a new K array, K prime, and usually K is twice pi by W, and the sigma K amount is the non-linearity. Then we can correct using this equation, and we have to correct over time. We have to take the corrected wavelength, and again that one will be used to correct again, and each time we have to check the error. If we see that error is reducing, and if we find that the fitted line of this phase line and the actual under phase line, if both of them match perfectly, then we can say that our wavelength is calibrated. Our wavelength is calibrated properly. So let's see how we can do that in MATLAB. So this is our code. This part is just to see the image, nothing to do with that. We are loading the data of the cover slip data that we took, and we are reading here, and first we are doing some rounding off here. Then if we need to flip the data, that means if we need to go from high wavelength to low wavelength or low wavelength to high wavelength based on the data acquisition, we have to flip the setup, flip the data. Then you can do the zero padding of the data to see the high spectral gain in frequency domain, so we can do that. So this is the base data. So this is the initial wavelength array. So this is our initial wavelength array. We converted this in K domain, and here are some of the parameters, how much wavelength pairing factor we will set as we need to detect the peak. So what will be the parameter? Peak will be mainly detected by the thresholding of SNR. So these are the parameters for the SNR. And finally we will run a while loop where we will set that three conditions. Current error should be less than the previous error, that is one condition, that should be true. Current error should be at least should be greater than the threshold, and the cycle should be less than some value, say 2000. So now what we need to do is we have to interpolate for the wavelength data. If you look at this command is here, so this PDK was the wavelength assignment, the wavelength that we got here, P wavelength that we assume, like initially we assume this is the P wavelength, and PD base is our data. Now this PD line K is the new way of calculating the K. That means we are transposing with the K value. Then we can see the spectrum, and we have to do the zero padding. So now our goal is to take the peak. As we mentioned that we have to take the peak out. So all this process is done just to find the left and right position of the peak. Then we select the peak out, we keep the peak out, and so this is just to view the spectrum. And here is the important part, that we are unwrapping the phase, and we are fully fitting the phase. This is the feed data, and we are subtracting the unwrapped phase minus fully fitted data, and we are finding the error. This is just to find the just fully fit the error. We are finding the new error just to make smoothing. Then here is the thing, we are using this error data to shift the K wavelength, and we are again doing the same step again and again. So here is the summary of all the steps. Here is the summary of all the steps. I can just recap again. That is, we are reading the dat file first, visual application, remove the fixed pattern noise and clean up both of the ends of the image. Then to match the wavelength, we can flip the data, then do the regular zero padding. That means do the FFT, then add some zero, then do the inverse FFT to increase the spectral gain. Again, you can re-clean the data and generate the initial wavelength to linearize your data. So these are one-time steps. These are one-time steps. Now what we have to do is we have to convert the initial wavelength in K array and linearize with our raw data that we take. So we have to linearize our data. Then we have to, as we need to pick the peak of the data, so we need to find the left and right peak position, and after that we will cut the peak position. So as I mentioned earlier, that why we are cutting the peak, because we are expecting that our wavelength is sinusoidal wavelength. If wavelength is sinusoidal wavelength, then it will generate peak in certain G position. So that's why we are cutting the peak. And we are analyzing only the data, those has a reasonable amount of intensity. That means if we look the spectrum, that means if you look at the spectrum, the two sides of the spectrum has a lower signal. So we are avoiding the lower signal, lower intensity signal. Then you have to unwrap the phase from the complex matrix of the data, and to match perfectly we have to find the polyfeed of the data. So two data here, we are unwrapping the phase and we are also polyfeeding the phase, and we are saying that the error is the unwrap phase minus the polyfeed value. This error value is used to estimate the new wavelength, that is new k, that new k array, and this new k array is fed again to the initial stage here, and it will go all the stages here. But where we will stop? We can stop on different condition that I mentioned in the code, that like this code will be run and come back again. So the exit loop condition is here. That means current three conditions it can match either these three conditions if the current error is less than the previous error. This is one condition. Second condition is current error is greater than some error threshold. We can also set some error threshold, and also we can say that how many cycle, if the n cycle is less than 2000 or whatever value you set. So these are the condition that these are the condition which are required to exit the loop. So mostly we have followed this paper, but there is some variation in this case. Especially the variation part is here, that how we are changing the array. Here we are taking the error value and we are dividing by P1. Here P1 is a coefficient value of P, and also we took a factor of 2, and then we shaped this wavelength, this amount, and did the interpolation, and again it will go. This is the new wavelength. So this is new k and this is the new wavelength, and this wavelength value, if you look at this wavelength value, will be used again here. This wavelength value will be again used here, just to go all the steps. So if I run the data, we can see that how it's changing, how the output is changing over different error. Say for example, for the first data, these are the spectrum, these are the peak we detected for the sinusoidal wave. This is after removal of DC, and here in the first cycle we can see the red one is our ideal one, and we are seeing that how much error. The blue one is indicating the error. The top two corner are the errors, has the issue that wavelength is not matched properly, and this is the error difference. You can see that the quantity is 15.28. Now if we go for the second iteration, if I click for the second iteration, so previous was 15.2, now is 15.03. So over time, as the time will pass, the error value will be decreased, and these two lines will be matched with each other. So that's the way to calculate the calibration file. Thank you very much for your patience to listen these things for so long time.